This is how we solve conservation of momentum problems. So conservation of momentum does tend to be challenging for students because not every momentum problem is the same. It depends on the type of collision. It depends if the blocks stick together. It depends if they bounce back. So when you see a momentum problem, you have to kind of think of it as a whole picture. I like to draw a before picture and an after picture just to demonstrate what's happening, and I think that's a really good tool. I also like to make a table and then fill in the gaps of what we don't know. So they're kind of like logic puzzles or logic puzzles or just puzzles in general. So if you're someone who likes to do that, you might like these type of problems, but they do require a little bit more thinking than perhaps we've seen at this point in physics. So let's get started. It says block A of mass 10 kilograms is traveling with a velocity of 8 meters per second. So here's my vector, 8 meters per second. My mass of block A is 10 kilograms. Block B of mass 4 kilograms is with a velocity of -5 meters per second. And that negative is really going to be important because that's indicating that it's traveling the opposite direction, so they're going to have a head-on collision. So we need to solve for the total momentum after the collision. So I'm going to make a table, and I highly recommend this strategy when solving momentum problems. So we're going to want to find the total momentum. We're going to need the momentum of car A, the momentum of car B, and then we're going to find the momentum before the collision, and then the momentum after the collision. And there's a few equations from the reference table we need to know. So if I scroll down here, zoom in a little bit. Momentum, I don't know why, but it's a P, a lowercase p stands for momentum. I guess because M was already used for mass, and so they were like, let's use lowercase p for momentum. I don't know. That's what they did. But here we go. So this is our momentum equation, mass times velocity. And then there's also this one here, momentum before equals momentum after. Both of these equations are going to be used to help us solve this problem. So if I scroll back up, all right, so we know momentum is mass times velocity. So we can use this to find the momentum for each section. So for block A, we know it's going to be 10 kilograms times 8 meters per second, which is going to give us 80 kilograms times meters per second. For block B, we know it's 4 kilograms times -5 meters per second, and that's going to give me -20 kilograms times meters per second. Then to get the total, we're going to add them, and since one of them is moving to the left and one of them is moving to the right, we end up subtracting them and we get a total of 60. Now, you may remember we said P before from the reference table equals P after. That's the conservation law. Whatever happened before has to equal what happens after. So we see conservation laws throughout science. We see it with conservation of energy, conservation of matter, conservation of charge. There's a lot of conservation laws in science, and momentum also happens to follow that. So if we know the momentum before, that means we also know the momentum after, and that's what the total momentum of the system is. So I think sometimes people forget it's the total momentum of the system. So not individual cars, because there is a collision, there's going to be some transfer of momentum, and we use that to solve that. But to answer this question, what is the total momentum? It is 60 kilograms times meters per second. So that's the answer to the first part. Okay, good. So we got that. Then we move on and it says if the velocity of block B, so this is after the collision, is 27.5 meters per second after the collision, what is the final velocity on A? So I'm going to draw an after picture. So we have 27.5 meters per second on block B, which is still 4 kilograms. It didn't break into pieces, so that's the same. Block A, we don't know which directions it's moving. Could still be moving to the right, could still be moving to the left. We don't know, but we do know that it's 10 kilograms still. So we can use the conservation of momentum. We can solve for the momentum of B after because we know the mass and we know the velocity. So that's what I'm going to do here. So it's going to be 4 kilograms times 27.5 meters per second. And when I do that math, I get 110 kilograms times meters per second. So then, with that in mind, I can solve for what goes on for block A, because basically block A plus block B has to equal 60. So it's kind of like x plus 110 has to equal 60. So simple algebra, we subtract on both sides, and I find that I get negative 50 for my momentum. Now, that's not what this is asking for. It's asking for the final velocity, but if we know the momentum of A, we know the mass of A, we can solve for the final velocity. So my final momentum was negative 50 kilograms times meters per second equals 10 kilograms times V. I'm going to divide by 10 kilograms on both sides. When I do that, I'm left with V equals negative 5 meters per second, and that is my answer. So this ended up bouncing back, and it's going backwards at negative 5 meters per second.